Every measurement device. So I need to actually have a screenshot of this thing. So I'm gonna just do print screen and send it over to your over here. So that is the question, so that we can find it later on. Okay. So one of the thing that we really need to understand that every measurement device, no matter what we're measuring, time, length, mass, force, momentum, energy, they all have a certain smallest value that they can decide in between. That smallest thing is what is sometimes called the precision of the device in regular terms, but precision in physics actually has a different set of meaning. It has a statistical explanation, which you'll learn about in AS, but not going there right now. For example, if we have a, let's say, sometimes the length of a shari is measured in hand, koi hat shari. I'm not sure if most of you or any of you have come across this thing. For example, 12 hat lamba shari is considered to be really comfortably wearable. Less than 10, less than 11 usually is not so good or not so preferred. So that's one measuring way. So ek hat means from the tip of the tallest finger of your hand to the end point of the elbow. That's one hand long. So over here, we are not going for any fraction. So here, the smallest measurement is itself the measurement length, that is ek hat. Then sometimes stuffs can be measured in terms of, let's say, yards. For example, cricket pitch for the cricket match is 22 yards long, which means if we have a yardstick that is one yard long, a yardstick basically means a stick that is 1 yard long, and we don't have any mark in between, which means the only length that it can actually measure is exactly 1 yard, because there is no mark in between. So we only know that from this measurement device, from one end to the last end, that measurement is exactly 1 yard. So if we are trying to mark out a cricket pitch for the standard measurement, we just have to use this thing along the same straight line 22 times over and over, and we can measure perfectly 22 yards line. So that's one way of measurement. And there can be devices which can measure even smaller than that. For example, the typical meter rule or half meter rule, or the usual meter rule that you have in your small scale, the 6-inch scale that comes with every geometry box, they actually have a measurement from 0 to 50. Now, if I just show you a picture, okay, this is a Faber-Castell 15 centimeter ruler. But if you have a good look, it is marked in inch on one side, and then it is marked on centimeter side on the other side. And because they have already written over here the word centimeter, it means that each of these smallest division actually represents 1 centimeter. So from 0 to 1, this is 1 centimeter. Then 1 to 2, 2 centimeter, 3 centimeter. So every part of these labeled lines are 1 centimeter each. And inside the 1 centimeter, we have these small fractions which are called the millimeter divisions. So, and that is the smallest fraction that you can measure out of a Faber-Castell ruler. So for example, this much is what we call the precision of meter rule, which is exactly 1 millimeter. This brings on to tell us that any measurement made with a meter rule, if properly mentioned, can be mentioned up to a precision of 1 millimeter, which means that, let's say, if we want to measure the length of an object, what we can do, we can align the left side of the object with this point, and then we can align it with the ruler. And then let's say it perfectly matches with one line of the meter rule. And then we can choose that value and write this. For example, an object can be, for example, the mark that I have done, the object that I have drawn over here is, let's say, 8.2 centimeter long. But that might not be like the case always. It is also possible sometimes an object might actually line up, let's say, somewhere in between these two lines. For example, let's say an object which is aligned with the 0 mark on the left, that's for sure. And let's say on the right side, that object shows up to be right here. Let's say it is coming at the halfway point over here. So let's say this is the end point of an object, another object. So it's continued over on the left side. So it's not perfectly aligning with neither 10.3 nor 10.4. So we do understand from the observation of this thing that this is more than, the length is more than 10.3, and it is I should actually can write this, that the length of the object is 10.3 centimeter less than length less than 10.4 centimeter. That's what we can see. But the question is, what should we mention? Should we choose any random number in between, or should we choose exactly the fraction half of this thing? The answer is no, because we cannot see or we cannot measure exactly how much fraction is it in between, because we don't have any marking for that. And the standard acceptable physics way, I mean, I shouldn't say physics, I mean the standard way to measure measurement for these cases is to express any of the values that it is aligned with. Now the standard is that, the procedure is that if we choose to go for the smaller number, let's say if we choose for this value, which I'm choosing the smaller number, that for all the upcoming further calculation, for example, for further measurement means, let's say we are trying to measure the volume of a rectangular glass block. So let's say we are given a rectangular glass block, and the experiment is that we have to measure the volume. So measuring the volume means we need the value of length, breadth, and height. So you have to measure the length in multiple sides, and eventually you can get the length, average it out. So for different measurement, you can have these things showing up in different places. For example, let's say for another case, whenever you're measuring the breadth or the width of the glass block, maybe that line shows up to be over here. So let's say from 0 centimeter, this much is the width, and let's say from 0 centimeter, this much is the length of the rectangular glass block. Now the typical protocol is that if we choose for our first measurement to be on the small side, then all of our upcoming readings should be also chosen for non-matching lines. That is, for non-matching alignments, we should preferably choose the smaller line. That's the rule of thumb. But sometimes this can be also chosen to be noted as for fraction. Now that's essentially what we're getting at, that if we want to measure accurately, that's the keyword, if we want to measure accurately fractions of 1 millimeter, how can we do that? Let's say so that's where we have some smaller measurement device. For example, we have Vernier calipers, and we have micrometer screw gauge. So first I'm going to explain Vernier calipers, then I'm going to go for the micrometer screw gauge. Vernier calipers look like this. The typical Vernier calipers that you will be using in your exam, which is most common, nice, is like this. This is a very detailed image, so which I really appreciate. Oh no, or oh yes. It's a really nice image. Okay, I can do one thing, which is the simplest way to go for it. Screenshot. Bam. So have a look. The way a Vernier calipers actually work is that This is what we call the fixed jaw, and this is what we call the movable jaw. This thing can clamp objects within itself. This thing can clamp objects. For hollow objects, we can place these two jaws on the inside of the object. For example, if you want to measure the inside diameter of a pipe or a hollow cylinder, we can use that upper jaws. These are called inside jaws. These are called outside jaws. And this one, have a look over here. This is the centimeter scale. So 0, 1, 2, 3, 4. That's the centimeter marking. And each of these smallest fractions over here represents 1 millimeter. This is what we call the main scale. And this sliding thing, that is this one, this is what we call the vernier scale. Now on the vernier scale, you don't see any length unit label. For example, here we can see the centimeter is printed, but we don't have any measurement printed over here. There is a reason. The reason is that this thing is actually going to measure a certain fraction of the centimeter. How much fraction? That is very easily calculable. That is what we call the Vernier constant. Vernier constant is sort of like, not sort of like, it's exactly the smallest length the Vernier scale can measure. Or in other words, I can say it's the step size of the Vernier caliper. For example, for a meter rule, the step size is exactly 1 millimeter. A meter rule can precisely measure between every millimeter. So 10.1 millimeter, 10.1 centimeter, 10.2 centimeter, 10.3 centimeters. So every 0.1 centimeter, which is essentially 1 millimeter, can be measured by meter rule properly. But if we want to measure, so 1 millimeter is sort of like the stepping size of the meter rule. Vernier scale has also something like of that sort, that how much is the smallest increment that a Vernier caliper can handle. That is called Vernier constant. And it's very easy to measure this. Vernier constant measured by the smallest fraction. Actually, I'm going to write smallest length on main scale divided by number of divisions in Vernier scale. And that is going to be 1 millimeter divided by 20, which gives us 0.05 millimeter. This actually means that this Vernier caliper is capable to measure with an increment size of 0.05 millimeter. Or in other words, I can say it can measure 20 individual incremental length within 1 millimeter space. So if you can somehow divide this any 1 millimeter space into 20 equal spacing, a Vernier caliper is capable to measure in between those positions. এইটুকু পর্যন্ত বুঝা গেছে কিনা? প্রমাণ? আচ্ছা, ওকে। সো এখানে একটা জিনিস খেয়াল করতে হবে, সেটা হচ্ছে what you should see over here. Here it is marked as 0. Then you have 1, 2, 3, 4. They are all marked on the even number of dots. Have a look at have a very careful look on the Vernier scale. Have a very good look. This is our first division, and this is our second division, but is marked as 1. This is our fourth division marked as 2. So what is actually happening? I mean, why do we have half the number of divisions over here, and what does it mean by showing 0 over here? Shouldn't this be 10? The idea is these people didn't want to clamp up the writing over here, something of this sort. So what they prefer to write a single digit number just to represent 20 divisions. So they did not label all the values, all the lines. They label all the other lines. So they labeled the first one 0. They didn't label the so they labeled the 0th one or starting one, which is 0. Then they did not label the first line. They labeled the second line as a single digit 1, so that they could cover the whole thing with up to the all the way up to 0. So this actually goes on to mean this is your 0 number line. This is your division number 1. This is division number 2, division number 3, division number 4, division number 5, division number 6. So what I'm trying to mean is that the printed marks over here actually represents division number to be double of that. For example, if in any case you're trying to take a reading of, let's say, this line, this one, this is on the label is at 7.5 for the scale, but in terms of division, that's going to be 7.5 multiplied by 2 equals to 15 division. This should be read as the 15th number division. The reason they did this kind of drawing is so that they didn't have to write 2 digits over here, because this whole space is not that long. It's actually quite small. So that we don't have to write 2 digits to marking. That's why they prefer to do it this way. So one thing that for observation, we should count exactly how many divisions we are taking for the reading. How do you take the reading? How do you take the reading? The reading can be taken like this. Let me show you another thing. Yes, 0.05 millimeter. Yes, did I write 0.5? Did I make a mistake? No, I did not. 1 by 20.
Yes, sir, but sir, doesn't it look a bit too big for 0.05 millimeters?
No. Here's the deal. Each of these gap does not mean 0.05 millimeter. We're going to utilize this scale in such a way that it would be able to measure for 0.05 fractions in between 1 millimeter. Physically, this much gap does not represent 0.05 millimeter. What this much gap means, I'm going to show you. Just give me a bit of a time. I will show you. Let me just find out this simulation. Okay. This is simulation which is all right. This is good. This is a good simulation. So we thank Professor Stefanelli from www.stefanelli.eng.br for such an amazing simulation. This is what, let's say what's happening over here. So okay, this is our main scale, and we're gonna place the object over here. Have a look what is happening. Whenever I'm closing this thing all together, try to have a very good look what is happening. When the 0 mark is perfectly aligned, with this scale, I should not actually zoom in. Let's zoom out. You should see that this first division is not perfectly aligned with the 2 millimeter mark. It's a bit smaller, and you can see that there are altogether 20 divisions over here, which are equal to 39 millimeters. Do you see that? This final 20th line is perfectly aligned with 39 millimeter. Can you see that? So there is a little bit of fraction over here. So how much small is each of these division is compared to a comparable number of division on the main scale is basically what the Vernier constant is. So in other words, I can tell you, if I just take a screenshot of this one and take it in our whiteboard. Vernier constant is, have a look. This one division, so I'm just gonna write this. 39 millimeter is equal to 40 division. Not 40 division, 20 division. Right?
Yes, sir.
So in that case, how much is the length of one division? So one division should be equals to 39 divided by 20, which is gonna be 1.995, I believe. I might be wrong. $1.95. 1.95 millimeter. So this much is 1.95 millimeter, which is apparently equal to this much size, but it's not exactly same. So that difference between 2 millimeter and 1.95 millimeter actually gives us the Vernier constant 0.05 millimeter. This is another way to measure the Vernier constant, but this is a bit complicated. So we usually go for the easier method, that the smallest mark on the main scale divided by number of divisions on the special scale, that gives us the Vernier constant as well. বুঝছো কি বলছি? এখানকার each division হচ্ছে 1.95 millimeter, not 0.05. It can measure 0.05 increment because of that small gap. If you wonder how does it measure, let me show you how does it measure. We're gonna let me go back to the simulation, which is right over here. Let's say we're going to place an object right over here. Take a good look what is happening. I'm zooming on over here. মনে করো যখন আমাদের ভ্যালুটা পারফেক্টলি এখানে আসে, মনে করো হচ্ছে let's say the zero mark is perfectly aligned with the 22 centimeter value. Okay, perfectly aligned with the 22 centimeter. 22 millimeters. So in this case, the object that is in between the jaws is exactly 22 millimeter. Now, what I want you to see, if I move this thing just a little, I just move this thing a very slight amount, and how much is that increment? If you have a good look, I'm not sure if you can see it. This line is perfectly aligned. Can you see? Can everybody see that? Whereas this line is not perfectly aligned, which means this main scale marking and this Vernier scale marking has a little bit of zap in between. Can you kids see that in your video device, whatever you're using, everyone? And if you see for this one is a bit more misaligned. This one is a bit more misaligned. The farther I go, the misalignment continues because the length of the Vernier scale is somewhat smaller than 2 millimeter, each 2 millimeter length of the main scale. And somewhere over here, this thing is totally mismatching. And over here, as you slowly go on to the right, this thing starts to match up once again by 1 short of millimeter. And finally, here we have once again at the last time 1 millimeter increase. So here is the catch. If I just move this Vernier scale by a single step, that is 0.05 millimeter, 0.05 millimeter, you see, we're going to have this alignment. If I move it by a bit more, we're going to have the second division in alignment. If we move it by a little bit more, we're going to have the third division in alignment. I actually moved to click twice, sorry. What am I doing? Yeah. Why am I pressing twice? I cannot make it come to the third alignment. I can. Okay. Here we have in the third alignment. Then we can get it to fourth. Then we can get it to fifth. Then we can get to sixth. So what we're going to see, what we're going to check for eventually when we will take measurement, is that we're going to try to put an object over here and try to find out which of these Vernier scale mark has the best alignment with any line on the main scale. So we're going to find out the line of this scale from 0, 1, 2, 3, 4, 5, 6, all the way up to 20 divisions. We're going to find out which number division is best aligned with any line on the main scale. The value on the main scale doesn't matter. The division that is perfectly aligned, that is what we are going for. Because what I want you to see, have a look. Whenever I have this thing right over here, do you see it? Dekho, this 22.0, right? This is 22.0 or 22 millimeters. I can move this Vernier scale for 20 individual distinguishable positions when this line, this zero line, moves from 22 to 23. So have a look. Here is 22.00, and then if I move it by only one step, I can figure out this small increment by observing this alignment. If I move it by a bit one more step to 22.10, I can observe that length increase by observing the second alignment. So by doing this, I can actually observe all the individual fractions within this 22 millimeter value all the way up to 23. And as I'm slowly reaching towards this thing, I mean, let's say whenever I am right about to get finished, you will see that this 19 number line is having the alignment. So slowly all the lines are going to get the alignments individually as this line, zero mark line, slowly moves from 22 to 23. And in how many individually distinguishable position can that stop? There are 20 individually distinguishable position, right? Because you can have individually 20 lines alignment to be observed. Do I make sense? Please ask question. I'm all for it.
Yes, Yes, sir. But could you, sir, just like show how we can actually like sir use the alignments to measure something?
Definitely, definitely. I'll go for that. Uh, okay, we are using this one already. My address bar and the browser are not helping. Okay, I'll show you. Don't worry. আচ্ছা, আমি আগে এই ফিগার থেকে আগে দেখাই, তাহলে তারপর হচ্ছে ফর্মুলা লিখে তোমাদের জন্য বুঝতে ইজিয়ার হবে। এখানে আমাদের টোটাল লেন্থ মেজার করার ফর্মুলাটা হচ্ছে এরকম। সো the total length that is always measured either by Vernier calipers or by micrometer screw gauge is given by main scale reading. I'm going to write in the short form main scale reading. You have the long forms in your book, so don't worry. Plus the special scale reading. Special scale in this case is the Vernier scale. For the micrometer screw gauge is going to be the circular scale. So that value is measured by Vernier scale division number multiplied by Vernier constant. You have to understand this is just a number of division. So what we do, we're going to place the object in between these two parts. So we're going to place the object that we want to measure in between the two jaws, and then we're going to squeeze the jaw to the left by minimal pressure. So we don't want this thing to become compressed. We just want to make sure the two jaws are perfectly touching each other. Then we're going to start to make an observation of this scale. For example, if we make an observation of this exact scale right now, let's try to find out what is happening. The main scale reading is always the left main scale value of the zero mark of the Vernier scale. Let me explain what this is. Have a look at this figure. This is the zero mark of the main scale. Do you see this? This is the zero mark of the, sorry, this is the zero mark of the Vernier scale. This is the zero mark of the Vernier scale. This zero mark is in between which two marks of the main scale? This one and this one, right? It simply means that this object that we have in between over here, I mean, this should be drawn a bit bigger. I mean, maybe a bit bigger would be good. This is supposed to touch both the sides. Okay, a bit more comfortable that way. So this value right over here, this one is 2.4 centimeter, and this one, which is on the right side of the, which is on the value of, on the right of the zero mark of the Vernier scale, this is 2.5 centimeter. The zero mark being over here actually means the total object is this much long, from zero to this zero. Object actual length হচ্ছে এইটুকু বড়, and if you wonder that why this zero is not starting from here, because this zero is not starting from exactly here, because of the construction of the whole thing. There's a little bit of gap from this position to this position. That gap is equally covered from this position to this position. That's a engineering solution for the ease of the use. Now what I want you to understand, the object is actually from this zero mark all the way to this zero mark long. Up to within this length we can measure this 2 centimeter directly from the main scale. What we cannot measure, or what we want to measure in the Vernier scale, is this extra part. The 2.4 centimeter পরে কতটুকু আছে? How much fraction of 1 millimeter does the object is going to measure? That's where the Vernier scale comes in. এই আইডিয়াটা বুঝছো কিনা? মানে হচ্ছে মেইন স্কেলের না, সরি, Vernier scale জিরো মার্ক, মেইন স্কেলের দুইটা দাগের মাঝখানে থাকবে টিপিক্যালি। Vernier scale জিরো মার্কের লেফটে মেইন স্কেলের যে মার্কটা থাকবে সেটা হচ্ছে আমাদের মেইন স্কেল রিডিং, আর এরপরে যতটুকু পার্ট বাকি আছে ওই পার্টটুকু মেজার করার জন্য আমরা এখন Vernier scale অবজারভেশন করব। এখন Vernier scale অবজারভেশনটা দেখি। আমাদেরকে ভালো করে খেয়াল করতে হবে যে এখানে যতগুলি 20টা যে লাইন আছে, we have total altogether 20 lines over here, so 0 through over 0. Which of these lines have best alignment with any line of the main scale? The 0, no. First one, no. No. More misalignment, more misalignment, more misalignment. Now from this point the alignment is about, this is getting closer, it's getting closer, it's getting closer, it's getting closer. Which one do you think has the best alignment? I think I marked it already. Do you see that this 7.5 marked division has the best alignment? And have a look over here, have a look over here, and then have a look over here. Which one? This one is supposed to be the best aligned line for the alignment, which means in this case our Vernier scale division is going to be 15 division. This one, 15 division. So এইটাকে দিয়ে আমরা ম্যাথটা করি, সেটা হচ্ছে the total length of the object is going to be 2.4 centimeter, this one the main scale reading, plus 15 multiplied by 0.05 millimeter. This was millimeter. If I want to make it into centimeter, I should divide it by 100. So which means this should be 0.005. I can actually write it over here, 0.005 centimeter. So it should be 0.005 centimeter. The reason I have to have both of the lengths in the same unit so that I can add together. I cannot add centimeter and millimeter. I can add centimeter and centimeter, or I can add millimeter and millimeter. So that's why I had to convert the Vernier constant to centimeter unit as well. So এখন ক্যালকুলেট করে দেখো টোটাল কত আসে। আমি কোথাও একটা ভুল করতেছি, কই জানি ভুল করতেছি আল্লাহ জানে। আচ্ছা না, ভুল করতেছে না। $2.475. I'm getting 2.475 centimeter. বলুন দেখো বুঝছো কিনা। What this goes on to show us that 2.4 up to 2.4 centimeter up to the millimeter value, which is 0.1 centimeter, up to the 2.4 centimeter, the main scale could make the measurement. How much is it additional to 2.4 centimeter or the last millimeter increment? That is measured by the Vernier scale, which is this much. এই হচ্ছে মেজারমেন্টের বেসিক প্রসিডিউর। বুঝা গেছে?
স্যার আমার একটা কোশ্চেন আছে।
প্লিজ।
স্যার আমাদের তো যে ভার্নিয়ার কনসেপ্ট সবসময় 0.05 মিলিমিটার না?
Well, for most devices that the laboratories in Bangladesh or in other countries that they use for O levels and A levels lab practices, they are usually always in 0. They always have 20 divisions on the Vernier scale, but it's not mandatory that there would be 20 divisions only. There can be 40 divisions, there can be 10 divisions. Vernier calipers can come in a lot of different variation. If you have something other than 20 divisions, then you have to calculate out the Vernier constant with that formula, 1 millimeter divided by the number of divisions. That will be your Vernier constant for that device. For example, if you have 10 divisions, it's going to be 1 millimeter divided by 10. If you have 40 divisions, it's going to be 1 millimeter divided by 40. So it can vary from device to device, but for most common devices, which is we have this one, the most common Vernier caliper that we use in our labs is this one. This is the most common version. Yeah. So the answer to your question is mostly yes, but there can be variation. If the examiners want there to be variation, they can bring about that variation. বুঝা গেছে?
জি স্যার।
ওকে, এটার মেজারমেন্ট প্রসিডিউরটা সব বুঝা গেছে কিনা? না বুঝা গেলে বলো, I'll help you understand, but it's important that you understood what happened over here. I want to move on to the micrometer screw gauge. এটা ক্লিয়ারলি বুঝা গেছে পোলামান? কেউ কিচ্ছু বলতেছে না। আচ্ছা, রাবেয়া এসআরএম এটা কে? Oh, this is Rabia Basri, right? What does SRM stand for? Acha, never mind. Acha, Scholastica. Okay. ঠিক আছে, সমস্যা নাই। Welcome to the class. If you have any question, feel free to ask and raise your hand or whatever does work for you. The next thing that I'm gonna discuss is micrometer screw gauge. Because you have understood how the device works, micrometer screw gauge is gonna make easier sense to you, although we don't have much time. I'm gonna try to explain it to you. If it doesn't happen within our time limit, no big deal. I'm gonna pick it up on the next class. But as long as we have the time, let's try to put our best effort to understand. রাইম, তুমি কি এই জিনিসটা বুঝছো যে আমরা কিভাবে 0.05 মিলিমিটার ইনক্রিমেন্টটা ডিটেক্ট করতেছি? You asked me that question. Ram actually is not in the channel anymore. Something happened. But the rest of you, did you understand that how are we detecting a small increment of 0.05 millimeter on the scale? How are we doing that?
Yes, sir.
Just to make sense of their observation, I bring about this animation, which is a very nice animation by this Dr. Stefanelli. Hail to him. Thanks to him. This is a nice one. So each individual alignment refers to one small increment of 0.05 millimeter, and that's how we do it. Okay, micrometer screw gauge. So let's just have a look at the individual parts over here that we have. My laptop crash korche. I hope it becomes uncrashed pretty soon. আমার গ্রাফিক্স কার্ড নষ্ট হয়ে গেছে, আমি এখন মাদারবোর্ডে ডিফল্ট গ্রাফিক্স কার্ড দিয়ে চালাই দিচ্ছি, কোনো আমার মোবাইলগুলো খেলতে পারতেছি না। সো আই এম রিয়েলি ডাউন অ্যাজ ওয়েল। হ্যাভিং এ মানে নন ওয়ার্কিং অর পার্শিয়ালি ওয়ার্কিং পিসি ইজ রিয়েলি never mind. So these are the name of the parts. This is called anvil. This is what we call, sometimes also called the fixed jaw. This is fixed in this position. We can actually reposition this thing if we want by a screw nut over here, but it's usually something that you are not going to do on your own. The lab teacher, if he feels like it, he's gonna reposition this for your purpose to set up different type of zeros over here. That's their job. And this is what we call a spindle. There's a U-shaped object, so you're gonna place the object in between over here. There is a main scale. Have a look over here. This central line, which is marked by multiple. So can we have? Have a look. This central line is what we call the datum line, or sometimes also called the reference line. Datum, D-A-T-U-M, which is the singular for data. This is something called the datum line, or something called the reference line. This is what we use to find out the actual division number on the circular scale. This is what we call the circular scale. And if you have a look over here, we don't have any marking over here, but this main scale is actually divided in millimeters, because here we have 0, and you can see on the top side 1, 2, 3, 4, 5. So after 5 division, we have 5, and each of these smallest division actually represents 1 millimeter. Interesting for you to observe, we also have some lower division marks at the midpoint of these millimeters. So practically speaking, this scale has half millimeter division as the smallest measuring mark. This is 0, 0.5, 1, 1.5, 2, 2.5. So উপরেগুলো হচ্ছে সব full integer mark value, আর নিচেগুলো হচ্ছে half millimeter value. So for this main scale, the reason they have marked this integer millimeter and half millimeter on two opposite sides is so that it's easier to observe. কারণ সবগুলোকে যদি আমরা একপাশে প্রিন্ট করতাম, লাইনগুলো অনেক কাছাকাছি চলে আসতো, অবজার্ভ করতে কষ্ট হতো। সো অবজারভেশনের সুবিধার জন্য লাইনগুলোকে দুই পাশে প্রিন্ট করা হয়েছে। আচ্ছা, এটা হচ্ছে আমাদের মেইন স্কেল। সো এখানে মেইন স্কেলের স্মলেস্ট ডিভিশন হচ্ছে half millimeter. That's the smallest increment that the main scale can handle. And on the circular scale, we usually have 50 division, and this is what is called the thimble. This is the thimble scale, or sometimes we call it the circular scale. And this is the ratchet. We usually use the ratchet to, there is a small auto lock mechanism, or which is called, sometimes called a clicker. The ratchet is used to place the object over here. We use our left hand, for example, to place the object over here, and our right hand should close it with the ratchet. Ratcheter মধ্যে একটা clicker আছে যে whenever the object, this spindle actually connects with the object that is placed in between the jaws, the ratchet starts to click. Having it clicked means the object is perfectly in between the jaws, and you don't have to squeeze it anymore. Because if we do it by the thimble, then we can actually, there is a possibility we can deform the object, because এটাকে অনেক টাইট করা possible. This device works on the concept of screw movement. So there is a screw inside. I wish I could show you the disassembled view of the lab. This doesn't work for me. আচ্ছা মাইক্রোমিটার স্ক্রু গজে ডিসঅ্যাসেম্বল ভিউ পরে কোন সময় বাই করে তোমাদের দাও এই যে পাইছি this is the individual different parts of the micrometer screw gauge. What you want to understand, there is a lock mechanism that exists over here, that's why there is a small hole. This whole thing is a hollow shaft, inside there is a thread, and this is the shaft that has a specific amount of thread mark over here. This is basically what works as a screw. That this screw is machined in a very precise manner so that the gap between each individual teeth, let's say this is the shaft on one side and on the other side this is the thing, the gap between each individual screw is exactly 0.5 millimeters. That's how it's machined. It's a very precise instrument, which means if we rotate the thimble scale, or if you rotate the ratchet, where is that thing? Yeah, let's say over here. If you rotate the ratchet by exactly one full rotation, okay. If we rotate it by one full rotation, if you rotate this ratchet by one full rotation, it means let's say we are seeing 0 over here, and then we're going to rotate by one full rotation. This whole thing is going to cover exactly half millimeter forward. So that's how the micrometer screw is going to work. Okay, many of you have a class right now, so I'll call it a day for the time being. Everyone, please do send your classwork. Take the picture and send it to my messenger directly. I'm calling it a day at this point because many of you have to leave, and we'll pick it up exactly from this point in the next class, inshallah. Assalamu alaikum.